Welcome to The Explainer. Today, we're diving into a real paradox in the world of high-strength aluminum, how the very act of joining it together can actually rob it of its strength. For these advanced materials, welding is really only half the story. The real challenge, that's what begins after the weld cools down. We're going to explore why this happens and the really clever fix engineers use to build all that strength right back up.
It's a strange question, right? You take two pieces of incredibly strong, super lightweight aluminum, you fuse them together with this intense heat, and then suddenly, the final structure is compromised. It just feels wrong. But this weakening is a huge hurdle for industries like automotive and shipbuilding, which absolutely depend on these advanced materials. Okay, so this chart right here shows us exactly what's going on. It's called a hardness profile, and it measures the material's strength as you move out from the center of the weld. You see that deep, W-shaped dip? That is a total collapse in strength. This softened area has a name, the heat-affected zone, or HAZ, and that is the heart of our problem. And look, this softening isn't some minor flaw. It's a fundamental change to the metal that can seriously compromise the structural integrity of the final product. We're not just melting metal here. We're essentially hitting a giant reset button on all its carefully engineered properties, right in the spot where we need strength the most. So to figure out the solution, we have to zoom in. I mean, way in. We need to see what's actually happening to the metal's internal structure during welding. It's really a story of creation and destruction. High-strength aluminum isn't strong just because it's aluminum. Its secret is a process called precipitation hardening. Now just imagine tiny, hard particles, these are called precipitates, forming inside the metal. They act like microscopic rebar reinforcing concrete, blocking things from moving around and giving the alloy its incredible strength.
And you can think of these formulas almost like different recipes for strength. Depending on the alloy series, say a 2000 or 7000, metallurgists will add different elements, maybe magnesium, zinc, or copper. These are what form those specific, unique strengthening particles we were just talking about. And it's these carefully created structures that are so incredibly vulnerable to the intense heat of a weld.
So here's exactly what goes wrong. That intense, totally uncontrolled thermal cycle of welding does three things. First, the heat gets so high it literally dissolves that microscopic rebar. Then, the weld cools down so fast that all those strengthening elements are just frozen in place with no time to reform into those helpful structures. And the result? Bam! You get that soft zone we saw in the graph. It's really a triple threat at the microscopic level. The heat can cause reversion. That's the complete dissolution of those good particles. Or it can cause overaging, where the particles get too big and coarse, making them way less effective. Or it could even form entirely new phases that just don't provide the same strength. The bottom line is, the material's internal architecture is a complete mess. So how in the world do we fight back against this weakening? Well, if an uncontrolled blast of heat caused the problem, maybe a very, very controlled application of heat could be the solution. And that controlled application of heat, well, it's a process called post-weld heat treatment, or PWHT for short. It's the key strategy that metallurgists use to take that reset material and carefully re-engineer the strength that was lost during the chaos of welding. But how does it actually work? Well, PWHT is a super precise two-step reheating process. First, the whole part gets heated up to dissolve any of those coarse, unhelpful structures that formed during the weld. Then, a very controlled aging cycle gives the strengthening elements the absolute perfect conditions, the right time and temperature to reform into that fine, strong, microscopic rebar structure that we need. The transformation is just night and day. Before the treatment, you've got a soft spot with a totally damaged microstructure and pretty poor performance. After PWHT, the hardness is recovered, that internal structure is rebuilt, and the original mechanical properties, they're restored. The data really tells the whole story here. On the left, you've got that deep W curve we saw earlier, the signature of a weakened weld. But just look at the graph on the right. After the heat treatment, that curve has almost completely flattened out. This shows a successful, uniform recovery of strength across the entire joint. It's amazing. But is post-weld heat treatment a perfect fix? In engineering, there are always trade-offs. So let's explore its limits and see where these simple process tweaks end and where true innovation really begins.
Yeah, PHT isn't a magic wand. For one, getting a full 100% strength recovery isn't always guaranteed. Plus, the heat treatment itself can actually warp the component. It can also cause the internal grains in the metal to grow, which can reduce the material's ductility, that's its ability to bend without breaking, which can make it more brittle. This brings us to a fundamental challenge, a classic trade-off in material science. You've got alloys like the 5000 series, which are super easy to weld but have lower strength, and then you have the high-performance 7000 series alloys. They're incredibly strong, but they are notoriously difficult to weld without them cracking. For decades, it's been a tough choice. Do you want weldability or do you want strength? This is where the future is headed. What if you didn't have to choose? This table shows a new novel alloy compared to the standard ones. Just look at the numbers. This novel alloy 4 has a yield strength of 404 MPa, even higher than the strong but fussy 7 series. But, and this is the key, it was designed to be easily welded. This is the absolute cutting edge of material science.
Which leaves us with a final, kind of provocative question for the future of manufacturing. Will the biggest breakthroughs come from refining our treatments to fix damage after it's already done, or from designing smarter alloys that avoid the problem in the first place? That's the challenge materials engineers are tackling right now.